This is a video over action potential. Now, the action potential occurs on the neuron on the axon, and more specifically on the axon, it occurs at the nodes of Ranvier. And what we're going to do is we're going to look at this node right here. We're going to say that's 1. We're going to say this node right here is 2, and this node right here is 3. Now, what we see right here is a zoomed in version of node 1, and we're going to record the voltages of node 1 here, node 2 there, and node 3 there as well. So if we get our system started by adding in our sodium and our potassium, the first thing we notice is sodium is on the outside of the cell. And the reason it's on the outside of the cell is due to the sodium-potassium pump, and potassium is on the inside of the cell, and that's also due to the sodium-potassium pump. Now, something really big we need to notice is that the cell, when it is at rest, is at a negative 70 millivolts. And what we call this is the resting potential. Resting potential. I'm just going to do rest P. So it's the resting potential of the membrane at the moment. Now the reason it's at a negative 70 millivolts is due to this minor potassium channel and this minor sodium channel. These are minor ones. These are the big ones that we'll be discussing in a moment. But let's just give the membrane a small jolt. Very small jolt. So what we see the voltage jump up, and then it goes back down. Now the reason it goes back down is watch this potassium molecule. Hopefully it hits it right. So, okay, there we go. You saw the potassium go from this side and go on this side. Remember, potassium is a positive, it's not a molecule, it's an ion. It's a cation, and it's positive. So you're taking something that is positive on this side, you're taking it away, so you're making this side more negative and this side more positive. And what voltage is the difference between how positive something is and how negative something else is. So when you transfer a positive thing and move it somewhere else, you're creating a voltage. So now we have this voltage of a negative 70 millivolts. But nothing happened with that little small jolt. Let's give it a massive jolt. Let's give it a relatively massive jolt. So now what we see the voltage climb, and you see it turned yellow right there. Right here is what we call the threshold. And that's at a negative 55 millivolts. Negative 55 millivolts. This negative 55 millivolts is very important because that's when the sodium channel opens. If you go back and rewind this video, you'll notice that these little blue rods right here, they're being not pushed up, but they're no longer being pushed down. These blue rods want to be up naturally. But since this side was very positive, these positive charges were pushing these blue rods down. So when the voltage decreased, to a negative 55 millivolts, these blue rods were able to be risen up. And the reason that they get pushed down is because they have arginine on them, which is a very positive amino acid. So the positive charges on arginine are being pushed down when this side is very positive. But it's no longer as positive anymore, so that allows the sodium channel to open. So now we have the sodium channel open right here. So threshold, and that's when the sodium channel opens. Open. That's sodium. So the sodium channel opens. Let's continue on watching. So now we have sodium going through this channel. And remember, sodium is a positive ion, so it's making this side negative and this side positive when it's traveling through. So it's decreasing the positivity on this side and increasing the negativity on this side. And if we keep on watching, what we'll notice is it will pass 0. There will no longer be a voltage across the membrane. So this is actually 0 volts. 0 volts. And then what we soon notice is the potassium pump opens. So the potassium pump opens, and it's finally fully open. It's finally fully open somewhere around right here. And we're going to say that's a positive 30 millivolts. So that's when the potassium pump opens. Potassium pump opens. Now something else that's really important is the sodium pump, or not pump, it's channel. The sodium channel now becomes inactive. If you go back again and watch this video, what you'll notice is this is time dependent. The sodium channel has time dependent functions on it. So this closes. The sodium channel no longer allows sodium through it anymore after about a millisecond of it being open. So that's something very unique about the sodium channel, is that it can deactivate itself, or it's actually inactive. So this right here, this little blue guy right here, this little blue ball right there, is the inactivation gate. So now we have the sodium channel inactive. So basically what we see is we see the potassium channel open and the sodium channel become inactive. Now since the potassium channel is open, what we have is we have potassium going through the potassium channel, making this side more positive and this side more negative. So the voltage is going to drop back down. But however, what we'll notice here, somewhere around here, the sodium channel begins to actually close. The sodium channel is now actually closing. Now before, the sodium channel was inactive. It was in the open position, but nothing could get through it. So that's a very important thing, because during this time, this sodium channel cannot be opened again until it closes. So what we call that the absolute limit of being able to have another action potential. So you cannot have another action potential between this time. It's absolutely impossible. Impossible. You cannot have it. So that's a way of preventing other action potentials from occurring. But that's not the only thing preventing action potentials from occurring either, because the potassium channel doesn't close for another little bit. Potassium channel doesn't close till right there. So now we have the potassium channel closing. The potassium channel is closing, and then the voltage slowly goes back to a negative 70 millivolts. And then again, that is due to, this time, sodium going through its minor channel. Minor, so we have sodium going through here. Or I'm sorry, that's potassium, not sodium. Or no, yep, there we go, sodium. So now we have sodium going through the membrane, and that causes the voltage to rise again to a negative 70 millivolts. So let's see if we just wait for one. Again, this is a low output channel, so it doesn't allow a lot of sodium to go through, just a very little about. So it goes relatively slowly. And that's important, because if we were to apply the same stimuli that we did here, that stimuli wouldn't be enough to cause another action potential. It'd be too low. It couldn't get high enough. So this is what we call the relative, I want to say refractive period time. Refractive period of time. I'll put it on the screen. I can't pronounce it for some reason, but it prevents another action potential from occurring. So even if we were to give another stimuli there, we could not have another action potential unless it was a massive stimuli. So this overshoot prevents another action potential from occurring unless it's massive. So we have the absolute prevention of an action potential in this area. So this area is an absolute prevention of the another action potential from occurring. And that's again because the sodium channel is already in the open position. It's just inactive. So let's just go through that one more time. So let's run through that one more time really quickly. So we'll give it the stimuli. The threshold will be met, allowing the sodium channel open. Now we're going to get all of our response. And notice something over here. This one just now hit the threshold. So now it's number two is finally having its sodium channels open. But number 3 hasn't had its sodium channels open yet either. So let's just keep an eye on that for a moment and just keep on going through. So number 1, sodium channels, and what we're looking at again is a zoomed up version of the node of Ranvier, this channel right here, or this node of Ranvier 1. So we'll keep on watching. Notice the inactivation gate is going towards the sodium channel, making the sodium channel now inactive. Now the big thing is, the sodium channel is open. Sodium just can't go through it. So how do we get an action potential? We get an action potential because the sodium channel opens. So if the sodium channel is already open, and sodium can't go through it, then you cannot have an action potential occur again. So that's why we don't have action potentials that do something like this. They do like that and go do something like that. They don't do that because the sodium channel is open, but it is inactive. So if we continue on watching, during this entire time, the sodium channel is open. It's still open. It's still completely open. And potassium is going through. And pretty soon, finally, the sodium channel starts to close. It pushes the little inactivation gate out and starts to close. At this point is when we can have the next action potential. No point sooner than this can you have another action potential. You just need an extremely strong stimuli, because the voltage at this area is at a negative 80 millivolts. So if we were to give it another stimuli, the exact same stimuli that we gave earlier, this exact same stimuli that we gave right here to get to this threshold, to reach that threshold, if we did that right now, what we would notice is it's not strong enough. It's simply not strong enough to reach the threshold. So the big thing is that you either get a big response or you don't get a response at all. You get the all or nothing response. And it's just going back to its negative 70 millivolts. So I think that's most of it. I guess one thing, just for the fun of it, and it's actually a really good reasoning. We can understand why potassium can't go through the sodium channel, because potassium is much larger than sodium. Potassium is approximately 30% bigger. Really good example. Where's a good one that has potassium and sodium right next to each other? I guess go with this one. You can clearly see potassium is much bigger. So that's why potassium cannot go through the sodium channel. But why can't, when the potassium channel is open, why can't sodium go through it? Right? So again, if we watched it one more time, we run it, have it run. So there we go. So now we have our potassium channel opening. Why can't this sodium ion go through this channel? Why can't it do that? It's small enough it can clearly fit through there. Why can't it? It has the same charge as potassium, but it's just smaller. So that's a really good question, really fun thing to find out. It's actually a really, really cool idea. But anyway, so now, I guess that's really everything. I guess one thing I would notice that this one is a little bit behind this one. It's a little bit behind that one. And this one is a little bit behind that one. Now, if you look closely, this yellow one represents the voltage generated at 2. Remember, this is 2 and this is 3, due to the voltages at 1. So the voltage at 3 is generated, or not generated, but exists that way due to the electrotonic force. So the electrotonic force goes across the entire membrane instantly, but the farther you're away from this source of the action potential, the weaker it is. So, I mean, because you would imagine you can't, I mean, just because a few, I mean, like this area would be highly positive, but something very far away wouldn't be as much as positive as it is. So the farther you're away from the action potential, the weaker it is. But this little climb in voltage is due to the action potential at 1. And then what we notice is we actually need 2 to cause an action potential, to get the voltage high enough to cause an action potential at 3. But the big thing is 3 cannot go back and activate an action potential at 1, because 1 is in its inactive state, right? Because 3 is at its highest voltage right here. It's at its highest voltage, but 1 is inactive. The sodium channels at 1 are inactive, so you cannot have another action potential. And even if it wasn't inactive, these potassium channels are open, and they're going to have a major effect because they're right next to it. Their effects are going to be just be enormous in comparison to what's happening at 5 miles down the road, or actually a few millimeters down the road. But I mean, so I guess that's the thing I'm trying to get across. I don't know how well I'm doing that, but so I guess that's everything.